Welcome. This is How to Tame a Mastodon, Lessons for Postgres at Scale. I'm Elizabeth Christensen.
I'm David Christensen.
We have the same last name and we work at the same company, so we thought we should do a talk together. Just kidding, we're actually married. And this was all my idea. So if it fails miserably, talk to David at the end. If you love it, come talk to me. This is not a talk on Mastodon, which has been a point of confusion for many people. This is also not a talk on the band Mastodon.
Much to my disappointment, but continue.
Yeah. This is actually a talk about a very large Postgres database, Mastodon. Just a little bit about us. I work in customer success at Crunchy Data. I do a lot of marketing and public-facing communications, and I organize the Kansas City Postgres user group, and I'm on Twitter at SQLLiz.
And I'm a principal database engineer at Crunchy Data. I do a lot of Postgres consulting, work with high availability Postgres, and have a full stack development background. I'm on Twitter as PG_DWC.
And I put a little, I have a slides up if you guys want to follow along at home. And I also have a little site at slideshare.net /ElizabethGarrett12 if you want to check those out. OK, so today we're going to talk a little bit about really big Postgres databases, and that involves a couple different things.
Sure. It's, you can talk about big data in terms of actual quantities of data, the actual database size itself. You can talk about like the number of transactions, if there's complications that come from having quite a few concurrent transactions. And you can also have large clusters that involve a number of replicas and how to manage all of those. So we'll be touching on things that affect those in all of this talk.
OK, so we're going to talk about a real life environment, a customer that we have that runs on the Crunchy Bridge platform. They have a transactional database. They have 100 developers and no DBAs, which used to be, you would never hear that, but I have heard that more in the last 2 years. They migrated to Crunchy Bridge from Heroku, and they have a 25 terabyte database growing all the time, 15 replicas, tons and tons of wall volume, tons and tons of transactions. So the way that we're going to kind of do this co-talk is that I'm going to sort of present some of the problems I'm having with this environment, and then David's going to give us some ideas of things that we can fix.
Our only other meme in this whole talk. So
you caught all the wall volume, right?
That was my initial reaction when we saw this client. So.
All right, so the first kind of place we're going to start is with things that are going on in this environment where you have one really big table. This is pretty common in Postgres, where you'll end up with one table that's just so much bigger than all your other tables, and that table needs a bunch of special care and sort of maintenance. So that's kind of where we're going to start. The first thing that I want to do to this giant table is add a column. If I do a normal add column, I know that it's going to lock my big table during the rewrite, but I don't want to do that because that's going to stop a bunch of transactions from processing. So what can I do to add a column?
Yeah, sure. Well, actually, as of Postgres 12, this is less of an issue. This will show up sometimes, only if you have like a functional default that's volatile. But Postgres 12 is still supported. So this is still kind of a concern. Basically, what we end up having to do is we have to split up our operation into smaller steps. So when you add a column normally, it takes a lock on the table, it adds the column, it rewrites the whole table. So what we're going to do instead is we're going to create it without the default. We're going to add the column, which will take a very brief lock. It'll add the necessary system column, but it won't rewrite the data. And then we're going to add the default itself, which doesn't change the data on disk, but it just tells the database, hey, this is what new records should have. And finally, we will update the table and set that to default, which will cause the whole table to be updated, but it does prevent that lock from keeping around while other people are prevented from accessing. So it really is a way of breaking things up and making it so you can add a column successfully without affecting availability on the table.
Okay, so let's say that I also want to add a constraint just for like validating things, making sure my application developers don't do anything weird. I want to put a constraint on a table. Same problem. I don't want to lock the table while it does the initial validation on the constraint.
Okay, well, as you might expect, this actually has a similar solution. What we're going to do is we're going to break this process up into two parts. So the first part we're going to do is we're going to create the constraint, but we're going to tell Postgres not to validate it with the not valid clause at the end of the alter table. What this means is that the constraint will get added quickly. It will start enforcing the constraint on new data, but it will not have to validate everything yet. Now, this does mean that this constraint is not totally enforcing on previous data, so we have to make a separate step where we run alter table validate constraint, and after we do that, it will go through the table, it will do the validation, and then if everything passes successfully, then it will enable that constraint fully.
Okay, so what about index creation? If I want to add an index on my really big table, it's gonna block writes during that index creation.
Yeah, so what we would do is, surprisingly, again, another drum beat, is we would break this up. We can use, Postgres has a built-in feature in this case that lets you break up this step. It's called create index concurrently. And what the concurrent index creation does is it first creates the basic part of the index, so new records will start inserting into the index. The old records are not yet in the index, and the index cannot be used for queries yet, but then in a separate step, it'll go through a pass where it will add the records that exist already into the index. Once that's done, it'll wait for any transactions that are open to complete, then it'll update the system table and say, hey, you can use this index now. So the create index concurrently is the big way to get through this piece.
Okay, let's say that I have looked around and taken a peek, and I've got a ton of indexes that aren't used. Do you have any suggestions for that?
Well, first of all, if you're dealing with a large cluster, you'll need to validate that those actually are unused, because each database, whether it's a primary or a replica, will have its own statistics. So a index that exists on one database may not be used on that database. It may be used on a different node. So you'll want to kind of compare all of the statistics on the usage just to make sure those are, in fact, not used. You can do that with the pgstat user indexes and the pgstat.io user indexes views. Those will tell you kind of how often things are used. When you can determine they are, in fact, not used, then you're able to go ahead and drop those indexes. You'll probably want to drop the index concurrently as well. So that is kind of the biggest thing there.
Okay, so I have been kind of looking at some of my queries and noticing that sometimes the indexes aren't used. So I have some parts of the data where it belongs to just a couple different clients, and I think that the data is skewed a little bit, and the indexes aren't being used, and it's just falling back to a sequential scan, which is super, super slow for some of the queries. How can I fix that?
Sure. Well, that is something where that situation will definitely occur. You can have, like you mentioned, some data that appears a lot. I think the cutoff's roughly 30%. If Postgres thinks it's going to have to scan 30% of the table, it's going to say, oh, let's go ahead and use a sequence scan instead, that it'll be a lot more efficient in terms of reading the table and just throwing out the rows that doesn't. So in this case, if you have multiple rows indexed, in addition to this key column, you can use a partial index where you create an index on the other columns and set a where clause for it to be the specific ID. This ensures that it'll use the index in those cases, and it tends to be just better in terms of overall maintenance there. That's called a partial index.
Okay, so I know that I need to be vacuuming. I know that that's an important part of cleaning up, deleted rows in my database, but I'm getting concerned that vacuum is running. It just seems to be running all the time. When it's running, I can see that there's a little bit of performance issue. What can I do to make sure that vacuum isn't just taking up all of the processes I have?
Well, definitely you want to make sure with a large database that you are tuning vacuum accordingly. So in this specific instance for this client, we had to update the auto vacuum workers. The default for that is 3. We've moved it to 6, basically because any one auto vacuum pass through the table takes that slot for the duration of the time. This gives us more slots to work with, and you're able to have better performance overall, since once you have tables vacuum, you can do things like index-only scans. We had some other tuning that we wanted to do for the vacuum. In general, a vacuum you want to run fairly frequently. The problem is with the default settings, a lot of those thresholds are based on percentage. So if you have large tables, the percentage of rows that need to change in order to kick off a vacuum are going to have to get bigger and bigger. If you have 100 million rows in a table and you have 1% that needs to change, that means 1 million needs to change before the next time it'll kick off an auto vacuum. So what we recommend doing in that case is tuning auto vacuum to use the scale factor of 0. The scale factor is the percentage that it takes, and then look at the actual thresholds, which is a fixed amount. So you would kind of look at the actual traffic that table is getting. You would then set that accordingly, and then we targeted about once a day for the tables, just to make sure that things were kind of staying up to date.
Okay, so we've just been talking a lot about this big table, and I just don't. This is causing a lot of issues, and we've talked about some of the things I can do with indexing and vacuuming and other things. But other than getting rid of data, what can I do to sort of make this an easier management in the future?
Well, I would say a lot of these large tables tend to be kind of log tables. I would say you have kind of data that's recent, that you kind of care about recently, and then you also have historical data that kind of needs to be there in case you check on it, but is not generally updated or anything like that. So that's something where we could recommend potentially looking at some partitioning. Now, partitioning sometimes people use in the context of query optimization, and while there can be some side effects that result in slightly more performant queries, I don't personally consider partitioning to be primarily optimization driven. It's more about data lifecycle management. So if you have like a requirement to keep 7 years of data online and you need to delete the previous year's data, you do that with a regular delete function, and that causes a lot of wall bloat. It causes a lot of just ongoing problems. You have to visit a lot of rows. Whereas if you use partitions, you can just detach the partition or drop it, and then you're able to do that quickly and effectively. So that's kind of one thing to think about when you're doing this designing. Now, partitioning is one of those areas, I like to call it the partitioner's paradox, where if you're coming into this and you realize you need partitioning, it's probably too late and you didn't plan it in. So you have quite a bit of data already. You do need to kind of work on how to get that from the non-partition table to the partition table. This generally ends up being a project. This is an area where tooling could definitely be improved, but there is a tool called pgpartman which can help you create and manage partitions on top of the native Postgres partitioning. But yeah, again, it's not a magic bullet. This is something that you just kind of have to work through, manually move data to those partitions. And then once it's there, you can kind of work with that. I think also, when people are in this situation, you can also consider sharding. There's a bunch of products out there that can help with that. There's Citus, there's TimescaleDB, there's other options for distributing amongst nodes.
Okay, thanks. And then, so the other question I have about this giant table is just in terms of space and how much space I'm using on disk. Is there anything that I can do to help with just wasted space, just making it smaller? Like obviously disk space is expensive, and obviously at the size that I'm at, if I can reduce it by even just a little bit, that'll really help us save some costs in terms of storage.
Sure. Well, this is something that is a little on the side of almost micro optimizations, but if you have the opportunity to do this, it can be worth looking into, and that's ordering of your specific table columns. So depending on what your data types are and the order of the columns, Postgres leaves padding in between fields to make it go out to, in all likelihood, 8-byte segments. So the way to optimize that is to basically start out with your large fixed size fields, use those first, and then move your way down. So if you had an 8-byte field, and then you had a 4-byte field, and then 3-byte field, or 2-byte field, 1-byte field, have those at the beginning, and then anything that's a variable sized field or a nullable field at the end. That can save you, in the degenerate case, 30% of your space just for normal column ordering. And so, you know, it's something that I wouldn't set out to do initially, but if you happen to be doing a migration, logical replication migration, something else that was able to afford some downtime or have to go through the process of copying all the data over, that's something you could actually do. You know, the more padding that's in the record, the more disk space it takes up, the more memory it takes up when you load it in the shared buffers, the higher wall volume for changes, and so on. So, like, while it is maybe micro-optimization, it does have a real impact.
Okay, so let's move on and talk a little bit about some of the challenges with this situation and tons of transactions. So we're generating tons of wall. I think, if I'm not mistaken, we're generating a wall segment every second.
I think 2 to 3 every second.
2 to 3 wall segments every second. Okay, so you know, talk to me a little bit about like how this works with the replay, how at this wall volume, what things we need to be looking at.
Sure. Well, by default, if you're just using a naive archive tool, Postgres calls this tool every time it needs to archive a wall segment. So in this case, 2 to 3 times a second, it will have to do whatever action it needs to do. You know, if it's copy to S3, if it's copied to a different server, it has to do that. It has to verify that it got there. It has to validate that. Then it'll come back to Postgres and say, okay, we've archived it. You're able to get rid of this wall file now. And then Postgres can say, okay, I can do that. I'm on to the next one. So as you can see, there's kind of a process that could definitely build up. If you were using a more naive backup tool, you could definitely get to a point where Postgres just cannot archive the wall fast enough as it's being generated. In this case, we're using PG Backrest. There's a number of other tools out there, but PG Backrest has a daemon mode and it has an async archive restore mode. So basically what it can do is it can kind of peek ahead. It can see, oh, this wall file's ready, but we also have 20 other wall files that are also ready, and it can do a bulk copy of all the data that's ready. So it can do that in one operation rather than 20 separate operations. So that kind of helps things keep up. That's a process that, yeah, it's the async archive and restore. Now, along with wall, when you create replicas based on this, in this volume, when Postgres has to create a new replica, it restores the base backup, which is kind of all the data files that exist on disk, and then it has to restore all of the wall that's been generated to this point. So Postgres is able to go through, this is unfortunately a single-threaded process in order to replay all the wall, but in your instance, I believe it took anywhere from 13 to 20 hours to generate a replica, just depending on when we kicked it off, because so much wall was being generated. So it would replay, get through the end, it would kind of get to a point where it would almost complete, but it would still just be 30 seconds behind, because by the time the wall archive failed to restore, the new wall file was there the next time. So it would kind of keep going, being 20, 30 seconds behind. So another thing that we had to do was basically kill it, switch it over into streaming mode when it got to that point, and at that point we had replicas that were caught up. I think another option that you could do, which would take a migration, would be changing the default wall segment size. We were using the default 16 megs, but you can always bump that, I think, as high as 1 gig. So that would be another option to look at.
Okay, so since some of these tables are so large and I have so many things going in, When we wrote this application, we used an ORM, and everything just defaulted to 4 bytes. And I'm scared that I'm going to run out of some IDs at some point. Can you tell me a little bit about what I need to do before I run out of IDs?
Well, sure, yeah, definitely you would want to be monitoring your ID values. That's a big initial step so you can kind of be aware of when problems are coming up. We've had clients, including yourself, come to us with this issue where they notice they're running out of IDs, and that gives you very little time to solve the issue. A short-term kind of quick fix, bag of tricks kind of thing is to be able to switch the ID sequence from positive to negative, because a lot of times you start out with positive integers for your IDs. If you can go to a negative integer and change the increment to -1, that can double your key space and buy you some time to deal with something else. You do have to validate that your application framework can deal with negative IDs. So that's a trick. The longer term solution is to just convert those from int4 fields to int8 using big serials. That does end up likely being a migration, although if it's just one table or so that you're dealing with, you can work on a way to get that to work without doing a migration. So.
Okay, so let's talk a little bit about connections. So we're using PG Bouncer. I think that we probably max out at, what is it? Is it 5,000 connections? What happens when we need more connections than this single PG Bouncer can give us?
Well, it depends really on how busy your PG Bouncer is. In your case, your PG Bouncer was not so much running out of connections, but it was running into issues with the quantity of data that was being shoveled through. So in this case, we ended up with PG Bouncer hitting 100% CPU. Postgres thought it was fairly busy, but not overwhelming. But from PG Bouncer's perspective, it was 100% used and no connections could go in or out. That resulted in latency slowdowns, everything taking a lot longer. Queries were delaying by 10 seconds and the like. So our solution to that was basically to do what we call multi-bouncer, which is where we have more than one PG Bouncer running against the same port using systemd. So essentially multiplexing multiple instances of PG Bouncer, so you can double your throughput even though it wasn't hitting the database at the same level. So here's a little diagram. You can see all the incoming requests. You can see multiple connection poolers connecting to individual Postgres backends, and that just makes for more efficient use of resources. In this case, PG Bouncer was the bottleneck and not the database.
Okay, let's talk a little bit about the read replicas that we have on our cluster. So we, brought on quite a few replicas to kind of reduce the read load on the primary. It's nice for redundancy. We can, put some fast queries on one place. We can do some reporting analytics. One of the things that's going on is we're really dealing with replicas at scale. We have so many of them now, we're over a dozen. What kind of ideas do you have for helping us manage this number of replicas?
Well, really it comes down to automation. If you have multiple replicas and you were in a self-hosted environment, you might recommend something like, Ansible or something to kind of maintain configs across multiple nodes. In this case, you're on Crunchy Bridge, so we can use our managed Postgres APIs to be able to spin up new replicas that are already done. Either way, you're going to want to have a centralized monitoring and data collection, whether that's through Datadog or through Prometheus or some other sort of ways where you can have one set of tools to kind of look at how everything's doing, health checks, et cetera.
Okay, so what do you think about using different replicas for different things?
Yeah, well, definitely you want to consider what your actual classes of replica are. It may be that you want to have a few queries or a few replicas that respond to queries quickly for like your web app. Maybe you want to have some analytics. They all would have different needs and different kind of performance characteristics. So you're going to have to kind of decide how that works. You're going to have to look at the individual stats on the machine to kind of figure out what needs to be done. Each one can have their own separate tuning, so the databases don't have to be tuned the same way. Either way, it's basically, we found that having a central point with all this data makes it easier to kind of configure and look at what things are in use.
Okay, so let's talk a little bit about replica and lag. So, if we don't have our replicas always up to date, this can cause an issue either with, third-party tools that are using the replicas or other things that are kind of downstream to the main machines that we're using.
Well, again, I would say this kind of comes back to defining the replicas for the role that you need them. I think the configuration and the tuning for a reporting application is going to be different than, if you have information that needs to be propagated for query balancing for things. So for ones where you need to have quick responses, I would tune to ensure that your statement timeout is set appropriately. If you don't anticipate ever needing a query to take longer than 2 seconds, go ahead and actually put it in there to make sure that query doesn't run longer. If you have something where the max standby archive delay or the max standby streaming delay are causing the wall not to replay quickly enough, this will help kind of ensure that the replica stays up to date, because I know it's very important to you as a client that these are as quick as possible. That does mean that your reporting replicas need to have different setup, though, because you're not going to be able to finish those in that way.
Okay, so let's talk a little bit about the reporting replicas that have, analytics and BI tools on them. So tell me what you think we should be doing there.
Well, one of the first things that you did is you guys had a service that you tried to use a logical replication system, and just with your wall volume and your transaction volume, that was something that was untenable. When it tried to copy your initial database out, things would time out, the disk would fill up. So using something that had logical replication was, in this case, not something that could be done. And the main problem was that impacts the primary. And what we decided to do, initially we tried setting a hot standby feedback to off on a replica, and then we decided we could go even further, and we could just set up a dedicated replica that wasn't streaming, was only pulling from the archive, that was dedicated to the analytics, and that meant that there was no way that you could impact the upstream at all, and so it was as isolated as it possibly could be. So I guess we can cover how we tamed the Mastodon overall. We minimized locking in our common table operations. We were smart about indexing, both creating our indexes concurrently and doing partial indexes. We tuned our primary to make sure that our vacuum was occurring as quickly as we can. We discussed the idea of partitioning. We talked about the schema for disk space based on padding. We looked at multi-bouncer, and then we planned how our replicas would be used. So I think we have a special thanks to our coworkers, Greg, Sabina, Mullane, who I work with on this client, and has helped work through a lot of things. Keith Fisk, who's reviewed things, sitting in the audience right there. And then our designer, Samantha Wheatley, who made these slides look a lot cooler than they were when I first wrote them. So.
And then we have a couple of links for you, things that we've published that are kind of in other pieces of content. We have a blog post on running multiple PG bouncers, and then a post on some of the large database problems, and then a post on the integer overflow and limits.
And we'll see if anybody has any questions out there.
Oh, I think so.
Mm-hmm. 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 I think that, yeah, that would have been right. That would have been an incorrect statement then.
So what's this supposed to be?
hot stand.
Okay, the question was to talk a little bit about hot standby feedback, like what it is, how it impacts things, or... Okay, so the hot standby feedback, basically what it does is when a replica is connected, it passes on information about kind of what rows are being accessed. So it acts as if it was a surrogate backend. So data where it needs it basically prevents vacuum from hitting and cleaning up rows that the replica needs to look at, so it stops query cancels from coming. So in this case, what we did is we had replicas that were running a long time, and they needed these things to complete. And these were 10, 12-hour queries. They kept getting canceled. So the initial way we were doing, because we didn't want to have 10 to 12 hours worth of things backing up, that was causing problems. So this was able to it was an initial approach to try to solve this problem, to prevent it from sending things to cancel. The problem, I think, ultimately came down to wraparound vacuums that were being forced to happen. So just based on the transaction volume, we had quite a few, every couple of hours an anti-wraparound vacuum would kick off. So we had to kind of manage things in a way that would make so this query wouldn't cancel while all these things were going on at the same time.
Well, thank you for the presentation. Just curious, when you did the optimization of table space by rearranging the column order, did it also help with performance?
I mean, it will. Okay, the question was whether the rearranged space would improve performance, I believe. Is that right?
Yeah.
In the way that if it's a smaller record, it'll just literally take less space. It'll fit on less pages. You can have more of that same record fit in the same space. It would improve. It wouldn't be a way that I would consider like the primary purpose of it, though. So kind of it would fall out a little bit. I don't know how measurable it would be.
Was somewhere in the middle of the record?
It shouldn't matter as long as there's nothing special in Postgres about the order of the primary key, so it doesn't have to be like the first column or something. So other than fitting in the same, like if you had all your, let's say it's a 4-byte int, you had some 8-byte ints ahead of it, that wouldn't affect anything. So. Anybody else?
There's one over there. That's fine, go ahead.
And you're saying for the wall replay? Or for the, okay. Some of that would be involved in looking at where the holdup is. So if it's something where it's on the local replica, it's already been copied over either through your wall receiver or pulling it through your archive. If it's there and it's not applying, some of that's going to depend on if there's something blocking the wall replay. So if you have queries that are accessing things that need to be replayed, in order to keep the snapshot open, it can't replace that until that query is done. So once the query is complete, then that can free that up. It can then replay the wall. So some of that will just come down to doing some analysis as to why it is. So if it's a delay in, let's say, you've got a very slow network or something, and there's a problem with your archive and it's not pulling the wall across, then that would be something that might be one cause, or it might be locks on the queries that are trying to replay. It could be another cause. I mean, kind of would come down to a specific case in your scenario, what that is. So those are a couple possibilities. So, anybody else? Okay. All right. Well, thanks, guys.